Hello everyone, nice to meet you. My name is Minli. I'm a PhD student from Lund University. Thank you very much for inviting me to give a talk at this workshop. This is a workshop Mosquito Study with Biospace. This is part 3. So I believe by now you have already finished the presentation with Hampus. So I will go into more details of how we're using biospace to help us with mosquito study and other insect studies. Some of you may have known our group already based on a system named ShineFlu LiDAR. We use this system to monitor insect behaviors. Recently, we have carried the system to a virgin forest in Ivory Coast. Currently, our group consists of the following members. Mikhail is a principal investigator and associate professor from Lund University. He is the supervisor of this group. Hampus, me, and the class were the PhD student of his, and we also have a master student named Isa at the moment. This is what our LiDAR system looks like from another angle, and here's what typical LiDAR result looks like. The LiDAR actively illuminating the air and by collecting the backscatter light from the insects when they're flying across the beam. With a recent study, we're capable of capturing 80,000 insect observations in 3 days' time in Sweden. We believe this record can easily be beaten if we collect the insect observation in any warm countries. LiDAR provides very high temporal and spatial resolution in its signals, which is something you can never achieve by manual sampling with, for example, sweep netting or Malay strap. This is what the typical LiDAR signal looks like, where figure A shows the LiDAR transects in the time and range map. We're able to see how long this observation was and at which distance we have observed it. LiDAR signal also provide information about apparent size of the insects, the optical cross-section of the insects, and we can also resolve the wind beat frequency of these insects, and it depends on the configuration you're using. In the example here, it was a polarization LiDAR, so we can also tell the polarization degree from the insect signals. In the example showing here, such signal has a wind beat frequency of 56 Hz. Even so, LiDAR is capable in providing so much useful features of the target insect, such as the sizing, wind beat frequency, or the polarization. We still need more information from it to actually pinpoint down which species of insects we're looking at. For example, there's a large amount of insects that share very similar wind beat frequencies. The figures over here showing the wind beat frequency span for different insect orders. Those values were collected from a massive literature studies. From this figure you can see for many orders of the insects, they actually share very similar wind beat frequencies. That means it has become really challenging if you detect some signal within certain wind beat frequency range. It is not possible to actually pinpoint down, say, which family or orders of insects is actually coming from, just based on wind beat frequency itself. And another issue is, for example, despite the LiDAR is capable of capturing the sizing and optical information of the insects, but in the example shown down here, the very same insects flying across LiDAR's beam depends on its orientation, flight speed, and heading directions. It may result in very different LiDAR signals, even though it was the very same insect flying through the beam. Therefore, we're looking forward to capturing more features of target insects, which is something more permanent and less dependent on the observation angles, for example, such as wind sickness, or melanin, or water pestilence. And this is something you can capture with a biospace. I hope those figures by now should look really familiar for you. This is similar to what you can see with biospace acquisitions. By placing the sample into the biospace and scan it, we are capable to capturing the body signal, which provide information about the optical cross-section, polarization, melanin, and pestilence. and it also provides signals about the winds, which contains wind interference patterns, wind thickness, polarization, and surface roughness. By changing the settings and wavelengths of the biospace, you can capture all those informations. Here I demonstrate to you how we can use those informations to help us to identify insect observations from our LiDAR signal. In the example shown here, on the most right-hand side are our current studies about the insect observation we see at the Taiyi Forest in Ivory Coast. For the very first insect signal and the last insect signal, they actually share very similar wind beat frequencies. Therefore, just as we mentioned, by wind beat frequency alone, we could not resolve which insect this is. However, based on the optical cross-section on the polarization informations, we're able to see, for example, the first observation has a really high polarizations and the last observation show really low degree polarizations. Therefore, the first insect show very specular wind signal and the last one should have a very diffuse wind signal. And based on the information about the wind beat frequency at the same time, we're able to see the first observation is most likely dragonfly and the last one is from Lepidopteras. And then when it comes to melanin and the water pestilence, at the moment we don't have any publication related to this. But in the example we're showing on the right-hand side, this is a spectrum we captured by scanning the mosquitoes, the female and the male mosquito when they're still fresh. With this simple model, we're able to see they have different water pestilence showing. And we're also thinking the water pestilence and melanin could relate it to the agings of the mosquitoes. By upgrade the fitting models to something much up to date, which is something demonstrated in Hampus' presentation, you can then acquire the melanin pestilence at the same time as you acquire the water pestilence. In the example we're showing here, we're able to map out the water pestilence, melanin pestilence within individual mosquitoes. And as we said, we believe those things are related to the agents of mosquito. It's something we're still investigating at the moment. But this is something you can do with a biospace if you have the right setting. And then when it comes to wind interference patterns, so first of all, as you see the example shown on the right-hand side, there's 4 different species and 2 sexes of the mosquitoes. They have different wing shapes and the wing sizing, and you can see the color, the structure color reflected from the wing are different among them. This structure color display on the wing is known as interference patterns. And the biospace, again with the correct wavelengths and the camera range, you will be able to capture these wind interference signals. In one of our other studies, which is related to hoverflies, we have noticed the hoverflies between different species and sex also show very different interference patterns. And we capture such a wind interference signals with a system similar to what biospace is, and we're able to resolve the wind interference signal into wind thickness, surface roughness, and polarization and other features. And as you can see on the most right-hand side, we are trying to see how much we can separate the species and sex, the solo based on the wing area and the thicknesses. We would say most of the species and sex are quite separate from the majority. In the same hoverfly studies, we investigated how much we can improve the accuracy of identifying the correct species and the sex of a hoverfly. We have noticed the wind beat frequency alone only has 13% success rate in identifying the correct sex and species. But when we including the wind information such as the wind thickness, wind roughness, and wind area, and how specular the signal is, we're capable to improve the identifying accuracy up to 91%. As we see the great promise by using the wind signals to help identify the sex and species in the hoverfly, then we perform the similar studies with mosquitoes. The 4 species of mosquitoes are shown over here, and we investigated for both sexes. At the moment, this result is also now published, but as you can see, similar to hoverfly, most of the species and the sex of mosquitoes are quite far away from each other, except few of them. And then we also investigated the allometry relation between the wing thickness and the wing area. As we can see, they are not an asymmetric relationship. What it means is when you have a very thick wing, you not necessarily have to have very large wing areas, and their relationships actually better explained with this allometry relationship. Here is an example of what different thickness of the mosquito wing and their corresponding reflectance spectrum will looks like within the chosen wavelength range. Here we have marked out 6 of the most common and commercially available laser diode wavelengths. They are 808, 980, 1050, 1320, 1550, and 1650. As you can see, different thicknesses, they have different reflectance on the chosen wavelength range, and by the chosen wavelengths you're using, you will get different reflectance values. And the figure on the right hand side is the reflectance value of each chosen wavelength, and it divided by each ratios. The figure on the right-hand side is an illustration about how well you can separate these 4 species of mosquitoes based on the wavelengths you choose. With the current results, we compare with the study we have conducted 5 years ago, and they are in highly agreement with each other. Therefore, it is highly promising to rely on the wing thicknesses and resolve the wing thickness difference with different wavelengths to tell different species and sex. And another amazing thing is, in other published studies, the thinnest wing has ever been literaturely documented was from Stavinga, and it was thinnest wing was about 350 nanometers. And in our case, we already see a wing thickness is much thinner by it. It was about 220 nanometers. Outside of identifying glassy wing insects like hoverfly and mosquitoes based on the wing interference signals, it is also possible to identify diffused wings like scale wings from moths and butterflies based on the wing surface roughnesses. Such a thing can also be accomplished with biospace, but again, you need to upgrade the wavelengths and the camera to the suitable range. If you're interested, you can look up in this study how we conduct the study and separate moth species based on the wing roughnesses. If you are interested, our group also have a YouTube channel where we upload and document most of our recent workshop and field works, and we have some tutorial as, for example, how to pin insects for biospace. If it's needed, you can check it out. Thank you very much for your attention. Wish you a great day. Please ask any questions.